So this is going to be similar to what we've done, but slightly different. We're still going to be finding volumes, so we're still doing something 3D, but we're not going to be finding volumes by spinning something, okay? We're going to find volumes by taking a cross-section, which is like a slice, and we're going to define what that cross-section shape is. So we're going to say all my slices are squares, or all my slices are triangles, or all my slices are semicircles, or all my slices are quarter circles, okay? And we're going to take that slice of something, and it's going to be like we set it straight down on the paper on top of the area between the two curves, okay? And if we put all those slices next to each other, it's almost like we're making a loaf of bread. Does that make sense? And then once we have all those slices next to each other, the loaf of bread has a volume, okay? So we are going to start off just remembering that the formula for volume, this is like way back when you talked about like cylinders or prisms, like right prisms, right what cylinder, whatever. Anyway, the volume of something, and I said this in the last video about volume, it's area of base times the height. Do you guys remember me saying that? Area of the base times the height. So if you have a cylinder like a Pringles can, the area of the base is a circle. So you would do the area of the base, which is the area of that circle, multiplied by the height, and that would give you the volume of a Pringles can. The area of a box, or the volume of a box of cereal, would be the area of that rectangle that forms the bottom of the box of cereal, multiplied by the height of the box of cereal, and that would tell you the volume that that box could hold. So when we look at volume, we just do area of the base multiplied by the height, okay? With the shapes that we're going to deal with, it's kind of like we're going to put them on their side. So we're going to say it's kind of like it's the area of the slice multiplied by the width, or the area of the piece of bread multiplied by how long the loaf is. And that would give you the volume of the loaf of bread. Does that make sense if we're kind of visualizing that a little bit? So what we're going to start with is we're going to look at the curve y equals the square root of x. And I'm going to show you guys, I just want you to be able to visualize this. So I'm going to show you guys what I mean by those slices. Okay? So it's kind of like the area that we're going to deal with. Here's what the square root graph looks like. And I'm going to bound it with the line y equals 0 and x equals 4. So y equals 0 is right here. That's the x-axis. X equals 4 is right there. So this is my shaded region right here. And so that means if I'm in terms of x, what's my integral going to be bounded by? 0 to 4. Okay. And then I'm going to take little slices of squares, and I'm going to put the slices of squares all the way across here. So the slice of this square right here is going to be a 4 by 4 square. The slice right in the middle is going to be a 2 by 2 square. I'm going to have a slice right here that's a 1 by 1 square. Does that make sense? If I'm like laying a bunch of squares next to each other, the squares are going to be varying in size because the side length of the square is coming from however far apart this is. Okay? So here's an actual like picture of what I have. These are squares. Do you guys see the squares? Okay, so right here I have my 4 by 4 square. Does that make sense? Here I have a 3 by 3 square because that's an x value of 3. Here I have a 2 by 2 square right there. And here's my 1 by 1 square. Okay, so it's kind of like I took slices out of a weird shape loaf of bread. Does that make sense? And then when I look at it, there's my like 3D shape right there. You guys see that? So do you see how it makes a solid? So I'm taking infinitely many squares and I'm putting them next to each other and I'm making a solid from that. Okay? So the volume of this is going to be the area of the square multiplied by the width. Okay? Area of the square multiplied by the width. Now the areas of the squares are changing, which is why we use an integral to represent this instead of just using old school algebra. Okay? All right. Here's another picture of the exact same thing but on my phone in this cool program. So here is the shape right here that we're dealing with, right? We have a square root graph. And here you can see like my squares. Are you able to see that okay? Get it off the shine. And then if I start adding more and more squares, do you guys see how it makes it more and more accurate? It's becoming more and more like a loaf of bread. Yeah. So there's my squares. And I've got a lot of them, so they're really small on this side. Do we see that? Okay. So the way that we figure this out, how do you find the area of a square? It's the side times the other side, right? Okay. Now to figure out the length of the side, I'm going to do top minus bottom. Do you see how that ties together? Okay. So the side length of the square is going to be the top curve minus the bottom curve, right? Because that tells you the width of that. And that's how I built my square. So I'm just reminding you, I said that this square was a 4 by 4 because it had an x value of 4, and I was doing, actually it would be a 2 by 2 square because the square root of 4 is 2. So that's my 2 by 2 square. All right. So I'm going to say that I'm going to call this S. S is going to be for my slice. All right, my slice, my cross section. So S is going to be the side length of the square. So S is top minus bottom. And because this is a square, I'm going to do side times side is side squared for the area of a square. Does that make sense? Okay, so I'm going to say this with square cross sections because it'll be different for different shapes. With square cross sections, I'm going to say top minus bottom squared dx. And that's going to tell me what my volume is. So let's go ahead and type this in our calculators and see what that volume should be.
Will we always have like top minus bottom squared? Like, will that always be a thing?
They won't always be squared because the shapes of the cross sections are not always going to be squares, but we're going to have specific formulas that we'll memorize for the different shapes, and so you'll always know what formula to use. Okay. It's 8. Everyone else get 8? Okay. Sorry, I'm changing my batteries.
I love how it's
All right, so we're going to say this is 8. Okay. We're going to look at some rectangles next. So with these rectangles, these are really tall rectangles. Okay. So the way that they did this, do you see the rectangles? The area of the base is going to be top curve minus bottom curve. And then this side is 3 times that. Always. Kind of. We'll have to think about it, okay? So each rectangle has this side is top minus bottom curve, and then this side of the rectangle is 3 times that length. Okay? So top minus bottom and then 3 times that length. So it's going to be kind of similar to the last picture we looked at, but our shape is a lot bigger. Do you guys see that? And they're made from rectangles instead of made from squares. Okay? Because that was the next shape I chose. Oh. Okay. All right. So this one we had, I'm going to go ahead and write square. We know that the area of a square is side times side, which is side squared. Next, we're going to go ahead and do a rectangle. And we're still going to have S as top minus bottom. But how do we find the area of a rectangle if we know that one side is top minus bottom and the other side is 3 of those? So we're going to say S times 3S. Does that make sense? So one side I figure out by top minus bottom. The other side I get by multiplying that side by 3. It's just 3 times. It's 3 times as tall as the base. The base is one measurement, the height is 3 times that measurement. Okay? So how could I simplify s times 3s? 3s squared. All right, so how is that going to change when I go ahead and find the integral? What am I going to change about the problem? Yeah, I've got 3 times top minus bottom squared dx. So it changes it a little bit.
I want to see what happens if the height is also a variable.
Well, this height was a variable. The height changed each time. Like another variable,
Yeah.
it doesn't change. Everything's always in terms of that s, that top minus bottom. Okay, what'd you guys get? Yeah. So, and that makes sense, right? Because that's like if you took this 3 and moved it to the front, then it's the exact same problem we just had with the 3 in front. Does that make sense?
So why
So-
are we getting different areas for the same curve?
We're getting different volumes
Oh, volume.
because we have different shapes that, like our loaves, our slices of bread are different shapes. And so these slices, if I compare these slices with these slices, the squares are much smaller, right?
Yes.
So my base area is the same, but these little slices are way bigger, and that's why my volume is so much bigger. Okay? Yeah.
So in like the question it'll specify if you want to do it by square root.
Yes. So in the problem, it has to specify what shape your cross section is, because otherwise you couldn't do the problem.
And then is this always when one side of the curve is touching the axis?
Yes. So one side of the curve has to be on that shaded area, because you have to know what one of your base sides are. You have to be able to get that S.
So it'll never be like the washer method.
It'll never, there's no such thing. This is literally, I'm not going to present a different situation. This is always how it goes. So the only way that these problems change is they give you a different shape to use. Okay? All right. I'm going to show you the triangle shape. So here's our triangles. See that? All right. So this is a problem where the base is one measurement and the height, I don't remember what this one was. Hold on. Talk amongst yourselves. I have to remember. Okay. You guys, I honestly don't remember what this one was supposed to be. So, somebody remind me, because this is a triangle. Somebody reminds me what the formula of a triangle is. Base times height divided by 2, or sometimes we say 1/2 times base times height. Okay. Now, I'm going to say that this one, the base, is one measurement. Do you guys see how we would calculate the base? How would I calculate that base? Top minus bottom. And I'm going to say that the height of this is 1/2 of the base. Okay? I'm going to say the height of this is 1/2 of the base. Okay? So let's go ahead and figure out how we write this on our notes. We have a triangle. The area of a triangle we know is 1/2 base times height. 1/2 base times height. So we said our base was our S value, right? Because S represents top minus bottom.
Okay.
And then our height is going to be 1/2 times our base. So what am I going to write next? Times 3/2 the base. Do we see how I did that? So this is a triangle where the base, the height is 1/2 times the base. And in my notes, I'm going to say this rectangle, the height was 3 times the base. Just so we have that in our notes. Okay.
So 1/2 base times 1/2 base.
The S is the base of the triangle, and the S is calculated by doing top minus bottom curve. And again, the reason we knew the base was S is because if we look at the base of the triangle, it's right along here, which is top curve minus bottom curve. Okay. All right. So what am I going to use in my integral if this is what I have? How can I simplify that? 3/4 s squared. Okay. So it's exactly the same problem we did before,
But 3/4 and stuff.
but 3/4 in front. Do you guys see how related these are to each other? They're all very similar. And that's because everything is going to be in terms of that top minus bottom, just like it was when we were doing the other volumes and just like it was when we were finding the area between two curves. So the reason these problems all feel similar is because the process is the same every time. You just have to think about what little part of the area of the base makes it a slightly different problem. Okay, so 3/4 times top minus bottom squared is going to give us what? 6? And that's because 3/4 of 8 is 6. Okay. All right, we're going to do one more. I made all these last year. All right. What shape is this? It's a semicircle. You guys see that? Shape of this is a semicircle. Okay. Why can't I do actual circles? Yeah, they're curved. It wouldn't make sense. I have to have something with a flat base to be able to use. Okay, so I can use quarter circles. I can use semicircles. I can't use actual circles. Okay. Could I use a star? No, I couldn't do a star. Could I do a hexagon? Yeah, that'd be kind of weird, but I could do it. Okay. I could do a trapezoid. I could do a weird star. Okay, so I've got different things I can do, but they have to have a flat base somewhere to be able to work. Okay, so I've got a semicircle. All right, the formula for a semicircle is pi r squared, right? Pi r squared. Okay, I want you guys to remember this formula is going to be our worst one. Okay, this is a formula you're going to have to memorize. Remember what S comes from. S is top minus bottom. Okay, S is top minus bottom. All right, so we have a circle. We're going to have half of a circle, which means we're going to do 1/2 of pi r squared. Okay, now this is the headache. Your S is top minus bottom, but what's your radius? It's half of S. You guys see that? So the area of a circle is pi r squared. We're going to do 1/2 of pi r squared. Okay, so I'm going to say 1/2 times pi times my radius squared. Does that make sense? 1/2 times my radius squared. My S value is top minus bottom. And what is my radius? Half of S. Okay. 1/2. My radius is 1/2 S. So the formula for doing a semicircle is 1/2 times pi times 1/2 S squared. It's not 1/4 though. Be careful about your form. It's 1/8. You guys see that? Because the 1/2 is squared, but you also have another 1/2. So it is 1/8 pi S squared. And that, for me, that feels confusing because I just want to say 1/2 pi S squared, but I have to remember what the S represented. And I have to find my radius, okay? So 1/8 pi S squared. All right, so now we're going to find our semicircle. So we have from 0 to 4 of what? Pi. Okay. Anyone know what that volume's going to be? It's going to just be pi. Yeah. Because the 1/8 and the pi get pulled out to the front, and we know that this part was just 8 because we know that from when we did the square. So it's 1/8 times pi times 8, which means that the volume is just pi. 3.14 is fine. That's what your calculator gave you. Okay. How are your brains handling this? Maybe not the best thing ever in the world, but kind of okay. All right, so now that we've kind of visualized some of this, we're just going to take notes on some of these shortcuts, okay? All right, so on your sheet of paper, that was us visualizing. Now we're going to get to the nitty-gritty of this. There's going to be some things that they say. So if you guys noticed, all of my shapes, my slices were the y coordinates, right? It was whatever y value is there. That's how I figured that out. That's why I'm plugging in x to find y. And if you notice, all these shapes are perpendicular to the x-axis. You guys see that? My slices are perpendicular to the x-axis. So if they tell you in the problem that your slices are perpendicular to the x-axis, then you do the problem in terms of x, and your s value is calculated by top minus bottom. Okay? So I'm going to go ahead and write that on my paper. If they say perpendicular to x-axis, then my s is top minus bottom, and I'm in terms of x. If they tell me that I am perpendicular to the y-axis, then how do I calculate my s? Right minus left, and I'm in terms of, okay?
After that, you would just do switch.
Okay. Now we have some different shapes for cross sections. So if we have a square, what's our formula? S squared. If we have a semicircle, what's our formula? 1/8 pi s squared. I would put a star next to that one. It's common, and you're going to have to make sure you memorize it. Okay? Because this one to me is a little bit counterintuitive. It makes sense when we looked at it, but later when we get past today and it's past Christmas break, it's going to be hard to just think of that one on your own. So that's a good one to memorize. The area of a triangle is 1/2 times base times height, and the base is going to be the s value. So we're going to say that's 1/2 s times h. The h is dependent on what they say in the problem. So when we did our example, I said that the height was 1.5 times the base. They could say the height is double the base. They could say the height is triple the base. They could say whatever they want about the height, so you're going to have to figure that out. Okay, so that means that you're going to plug something in for that h value. Okay? Yeah, 1/2 sh. All right. We have equilateral triangle. And this one is √3/4 s squared. And the reason that that's the formula is because if you look up the area of an equilateral triangle, the height of an equilateral triangle is √3/2 times the base. So this is just kind of like we said, 1/2 base times height, and we already knew what the ratio of the height would be if the triangle was equilateral, okay? So this is another one. I'd star semicircle, I would star equilateral triangle. Those are common ones that you're going to have to memorize because they're weird, okay? So this is saying 1/2 times the base of s times √3/2 times s, and that's because that's the relationship between a base and a height of an equilateral triangle. All right, so that's where that came from, but you're just going to memorize this. This is a pretty common one, okay? And then the last one I'm going to say is a rectangle. and that is base times height, which is going to be S times H. And the H can change. So like the rectangle we did, we said the height was 3 times the base. So we had S times 3S. But they could say the height is twice the base, or they could say the height is 5 times the base. They could say whatever they want, okay? They could say the height is 5 every single time, and then it would just be S times 5, okay? All right, how do we feel about those formulas? We can see how to work them? Okay. So I think that was everything. Let's go ahead and do some examples. Okay. So here's a picture, and what I've done is I've taken the same situation and then done a ton of different cross sections, okay? So we have a square, we have a rectangle with a height of 2, where the rectangle's height is always 2. It never changes, it's just always 2. We have a semicircle. If you flip it over, we've got a quarter circle, an equilateral triangle, a triangle with a height that is 1/4 the length of the base. We got a trapezoid, okay? So we've got shapes on here that I did not give you formulas for, which means that at some point we're going to have to start to think about our formulas for our shapes, okay? All right, so let's start off with just setting up the original problem. It says that we have the region bounded by x equals y squared, which, as you can see, is a parabola that goes on the x-axis instead of the y-axis. You guys see that? It's a sideways parabola. And the line x equals 9, so that's the vertical line, x equals 9. So it's kind of like, I drew it 3D, so it's kind of like the, okay, so we can see that. Find the volume of the solid that has R as its base, and every cross-section is by a plane that's perpendicular to the x-axis. So are we writing these in terms of x or in terms of y? In terms of x, okay? All of these are in terms of x because we are perpendicular to the x-axis, okay? So I'm going to write in terms of x. Now, what's the problem with how they gave us this situation? It's in terms of y. So that means that we need to take this right here and we need to rewrite it. So I have x equals y squared. How do I rewrite that in terms of x? Square root. Y equals, and what do I do whenever I square root something? Plus or minus. I've got plus and minus square root of x. So what that means is that the top part of this is y equals positive square root x. The bottom of this is y equals negative square root x. Okay? Now, before we can go any further, what do we have to figure out? Well, we know that, right? This is going to be, what's the bounds for our integral? 0 to 9. So that part's not bad. They gave us that part pretty easily. Our bounds for our integral is 0 to 9. But what shows up in every single equation? The s. The s. How do we figure out s? Top minus bottom. Okay, so s equals top minus bottom. If we look at this picture, what do we get when we do top minus bottom? Well, it's just the shaded region. So here's our shaded region, right? And it's top minus bottom. So it is square root x minus negative square root x. So last time we had cut it off right there so that our top minus bottom was square root x minus 0. Now we're using the other side of that shape. So we're doing top minus bottom is square root x minus negative square root x. Does that make sense how I got that top minus bottom? Okay? Because it's two sides of the parabola. So square root x minus negative square root x is what? 2 square root x. Okay, so this is 2 square root x. All right, let's go ahead and set up the first one. So we have the integral from 0 to 9. We know that our top minus bottom is 2 square roots of x. And what's the formula for a square?
S squared.
S squared. So here's my s. I'm doing s squared dx. Yeah, once you find s, it really is not bad. As long as they gave you the formula. If not, then you have to use your brain a little bit. Okay, what do we get for this one? It'd be 162. Did you type it in?
No, I was just wondering why we couldn't just like plug it in.
We did. She plugged it in her calculator.
Well, no, like why couldn't we do it like by hand?
You could do it by hand.
So 2 times the square root of 9 squared.
You have to do the antiderivative,
That's why.
right? Yeah. So if you were to do this by hand, you'd have to like simplify that and then make sure you were doing the antiderivative steps. Yeah.
Okay.
Okay. All right, let's look at a rectangle with a height of 2. So what's going to be the formula for a rectangle with a height of 2? Yeah, it's going to be base times height. The base is the s value. The height is always 2. The height never changes. It's just always 2. So we're going to say it's from 0 to 9 of s times 2. So our s is 2 square root x times 2 dx. 72. Okay. Let's try the next one, a semicircle. What's the formula for that? Okay. So we're going to say the integral, I know I said that real weird, thanks for not laughing, from 0 to 9 of 1/8 pi.
2 square root of x.
Okay, please don't yell at the answer because some of us are slow and want to do it by ourselves.
Okay. But she said it with a certain voice because she knew she was doing a bad thing. She knew it. She's like, I'm a bad person, I'm doing this anyway.
No, I'd rather not.
Say it again.
Friend.
63.617. Did you get your parentheses in the right place and get your squared and get your square root and all that? All right, go ahead and flip it over. Now we have a quarter circle, so we have to figure out what the area of the base should be. So now it feels like, listen carefully, because you could be tricked by this. It feels like, well, if we had a half circle, then let's just do that times 1/2 and we get a quarter circle. But look at your radius. How's your radius defined on this problem? It's different than the radius of the semicircle. But look at your radius. Is your radius 1/2 s? No, what's your radius? It's just s. The radius of your circle is just s. Do you see that? This is the radius right here. Ooh, that's the whole radius. Look back at your semicircle. Doesn't your quarter circle look a lot like it would be from a bigger circle? Do you guys see how your quarter circle looks like a much bigger circle than your semicircle? For the semicircle, the radius is right here. The radius is only 1/2 of the s on a semicircle. On a quarter circle, the radius is the whole s. Okay? So how do we find the area of 1/4 of a circle?
1/2 pi
It,
s.
it'd be 1/4 pi r squared, right? 1/4 of a circle would be 1/4 pi r squared. And this time the r is just the same as s. So it's going to be 1/4 pi s squared. So everything else kind of works normal. The semicircle really is just the weird one. Okay? Quarter circle is easier than semicircle because the quarter circle at least makes sense. Okay? All right, so we have our interval from 0 to 9 of our quarter circle.
No, I haven't written it down yet.
The old calculation changes a little bit.
She didn't finish the first calculation. That one hurts. Hey, at least I didn't show the answer.
Never regrets. Yes.
And it'd be 4 or 5 depending on truncated versus rounding. Okay. Truncated is when you just cut it off. And you don't worry about rounding. All right. Equilateral triangle. Have we memorized it yet?
There's like
Ben, you're awake.
I got home at like 2 this right.
Oh, I believe it.
South Carolina. Yeah. But
70.14 maybe.
like
140.
it's only supposed to take 8 hours. It took a solid like 10 to 11. We caught traffic like South
70.1.
Carolina.
I keep killing it.
It was great.
Yeah, don't forget the DX. It's frustrating when you're like, I plugged it in right. Why is there an error message? You missed the X. Yeah.
That's what happens when you
I
what?
think the most frustrating.
I'm talking to that table.
Just use the old equation we typed in instead of typing the whole thing in again.
That's what I do, Isaiah.
Exactly.
Smart thinking.
Until you get it wrong.
Until you get it wrong.
All right. We have a triangle with a height that is equal to 1/4 the length of the base.
Look at how sad it looks.
It is a sad little triangle. Okay, so what's the formula? We have 1/2 times base. What do I put for base? Yeah, so my S value times my height, which is 1/4 of S. So I have 1/2 times base times height. Shh, Ben, shh. I want you to go back to sleep because now you're just talking. Base is S, height is 1/4 S. What?
Why is it?
And that's because they told you the base is the same 1/4 the length of the base. So what we're integrating now is from 0 to 9. If I multiply all of that out, I get 1/8 2 square root of x squared. Yep, so 1/8 s squared. Huh?
On the AP exam, like if we were asked about this, would we be able, like, are we going to get to the point where we're able to like look at that and just be able to draw?
Yeah, there's a point like you'll do. Hey guys, I need you to listen carefully. A really common FRQ for this unit is 3 parts. They draw a shape of a top curve and a bottom curve. And they say, find the area of the region. So that's just basic area between two curves. Integral, top minus bottom. Then they say, revolve it around a line. Then you're doing your volume of revolution. And it could be a disk method, it could be a washer method. Then they say, find the volume if it's perpendicular to the x-axis and the cross sections are squares. So they do FRQs where they hit all three of these. Okay, all three of the things we've learned. Very common. That's a very common FRQ, is to hit all three of those things. Okay? All right.
Are they more likely to use the squares more than anything else?
I've noticed squares, equilateral triangles, and semicircles. Those are the three that I've really noticed showing up. I haven't looked at it, but probably. Okay. All right. Let's look at the trapezoid, because this one, I think, in my opinion, is the hardest one on the page because you actually have to use your brain. Okay? So somebody remind me, let's not even look at the picture. How do we find the area of a trapezoid?
Base 1 plus half base 2.
Okay, base 1 plus base 2. I heard that.
Times 1/2 times height.
Okay, 1/2 times height. Okay? So when we look at the picture, which part of the picture matches which part of this? Okay, base 1 is S. Okay? So I'm going to go ahead and replace base 1 with S. Now I got to figure, I know the 1/2 is going to be there. Now I got to figure out the rest. Upper base is 1/2 the length of the lower base. So 1/2 S. Okay. So we said this is our lower base, this is our upper base. And then the length, 1/2 the length of the lower base is the height, so then we have the height is 1/4 S. Okay. So if I simplify this, I have 1/8 S times 3/2 S, which is 3/16
S squared.
Okay. So do you see how we thought through that to figure out what it would be with our S's? How did we know that the what to choose for S? Which side represented S? Yeah, we just looked at where our top minus bottom happened to be, and then we made the rest of the formula work within that. Okay, so we have the integral from 0 to 9 of 3/16 S squared.
Basically, if you were given like a problem without a lot, like without the context that we have, all we have to do is find the base of a square and then apply that to everything else because the side.
Yeah. So the important thing here is to figure out your S. And then first of all, figure out your S. Second of all, know what the area of that shape is. Figure out the S based on top curve minus bottom curve or right curve minus left curve. Okay?